Okay, so we have properties of logarithms. So the first group are change of base formula, and that's needed because our calculators and in the old days books of logarithms didn't have all the bases involved. So you need to be able to figure out the base of logarithms that are other than base 10 or base e. So we can either use base e or the base 10. We'll do both of them, just show you it does work. Okay, so the first problem, log base 9 of 0.4. So what you do is you take the log to the base 10 of 0.4 and divide by the log to the base 10 of 9. Or you could take the natural, so or also the log base 9 of 0.4 is the natural log of 0.4 divided by the natural log of 9. And if we did this right, we should get the same answer. So we'll see what happens. Okay, so log base 10, which is just log of 0.4 divided by log of 9. And we get negative 0.417. And if we take the natural log of 0.4 divided by the natural log of 9, we get negative 0.417. So it does work. So the next one is log base 3 of 0.015. That's the same as log base 10 of 0.015 divided by log base 10 of 3. Or we could take the natural log of 0.015 and divide by the natural log of 3. So let's see what we get. So log base 10 of 0.015 divided by log to the base 10 of 3 is negative 3.82. And the natural log of 0.015 divided by the natural log of 3 is negative 3.82. Which one to use? It's up to you. Okay, the next thing, use the properties of logarithms to expand the expression as a sum, difference, or a constant multiple of logarithms. So the three rules are the natural log of the product of two quantities is the natural log of the first quantity plus the natural log of the second one. The natural log of a over b, or a divided by b, is the natural log of a minus the natural log of b. And the natural log of a to the b power is b times the natural log. And I'm using natural logs, but it doesn't matter what base you're in. So if you're in base 4, you use base 4. So it's b times the natural log of a. So you can take the exponent inside and move it out as a constant multiple times the natural log. Okay, so those are the rules. So here we've got a product, so it's like the first case. So what we can say is the log base 4 of 5x is the log base 4 of 5 plus the log base 4 of x. Okay, the next one we have a quotient, so we're going to use this one. So we can say log base 10 of y divided by 2 is log base 10 of y minus the log base 10 of 2, because we have a over b, and we just plug in a and b. Okay, number 5 is log base 6 of 1 over z cubed. So we have log base 6 of, so in this case we're going to have to use two of the rules, but we'll use the quotient rule first. So you get the log base 6 of 1 minus the log base 6 of z cubed. But the log to any base of 1 is 0, so that just becomes 0. And then we could use this rule here. Natural log of a to the b is b times the natural log of a. So the multiplier, the exponent is 3, so that comes out front. So you get that result. Okay, natural log of z, square root of z. So when you have square roots, cube roots, the first thing you have to do is convert the square root to a fractional exponent. So what if it's a square root, it's the second root. So you divide 1 by the second root. If it was the cube root, you'd have a little cube thing here. You'd have z to the 1/3. So I'm just converting terminology here. Square root is the same as a fractional exponent. And then because you have an exponent, you can use rule number 3. So you can bring that exponent out front. So you get 1/3 the natural log of z. Now if you have more than one thing happening, so I've got something multiplied by something multiplied by something, you can, if you're multiplying stuff together, you just add the logarithms together. So you're going to have log base 10 of 4 for that part, plus log base 10 of x squared, plus log base 10 of y. So I'm using the product rule to break each one of these apart. Now, sometimes if you still have an exponent, which I do, you can then use the third rule to bring that exponent out. So the second term becomes 2 times log base 10 of x instead of log base 10 of x squared. The last thing stays the same because it's just y by itself, so there's not much you can do beyond that. Okay, I think we have some more examples here. Yep. So you can see how many we're doing, and this turns out to be extremely important in calculus. So we use these properties of logarithms a lot. Okay, so here we have two things we've got to take care of. One is we've got to change this square root to a fractional exponent. So I change that to the 1/2 power. And I'm dividing by, yeah, the question is that all the way around the whole thing? I think it is. Maybe not. I have to look at the book. Well, let's just assume that it's not. So in this case, I'm just doing the log. Yeah, it must be the whole thing. So I'm taking the logarithm of the whole thing. The square root's not of that part. So I am doing the whole thing. So this is the numerator. So because it's in the numerator, I put that with a positive sign out in front. And because this is in the denominator, I subtract. But I still have this exponent, so I want to get rid of the exponent. So I'm going to bring that out. Now, a lot of people are tempted to go too far and try to separate these, but these rules do not work for subtraction or addition. They only work for multiplication. So here, I'm dividing this whole thing by 9. So that's why I can use the rule. But when I have just a minus 1, then I can't use it, and that's as far as you can go. But this exponent here applied to both terms, the whole term, so that's why I can bring it out. If I had a squared minus 1, then I couldn't do it. I couldn't bring the 2 out. This exponent has to apply to the whole expression inside there. Okay, number 9. That was number 8. Number 9. So again, I'm going to change the square root into a fractional exponent. And I haven't used any properties of logarithms. It's just using the properties of relating the square root to the fractional exponent. Now, before I do this, I could just apply this to both terms. So x squared to the 1/2 power, you multiply the exponents together. So you get x. And here, 3 times 1/2, I get y to the 3/2 power. Okay, so that's just kind of cleaning that up to start with. Now I didn't have to do this. I could treat this as a quotient with an exponent, but it's easier just to do this inside. Okay, so I have this term which is in the numerator, and I have this term which is in the denominator. So this one's done because there's no exponent, but here I do have an exponent. So I go one step more, bring that exponent out, and end up with that. Okay, number 10. So I've got this in the numerator, these two both in the denominator. So if it's in the numerator, it's positive quantity, and if it's in the denominator, it's a negative quantity. So I'm going to have positive log base 5 of x squared minus, because it's in the denominator, log base 5 of y squared. And then the z is also in the denominator, so it's going to be log base 5 of z cubed. So that splits all those three parts of the product up. But these exponents apply to each individual one specifically, so I let those follow as they are, 2, 2, and 3. 2, 2, 3. Now I can use the, because this applies to the entire argument, x, so I can bring that outside. In the same way here, I can bring the 2 outside. And I can bring the 3 outside. So that's your final answer. Okay, so those are all examples of expanding out logarithms. Now the other way is to condense logarithms. And sometimes you can and sometimes you can't do something. So this one, there's really nothing you can do, okay? I'm not even sure why it's in there. So 12, it's just 2 times log base 2 of x plus 4. It's not like I can break it. I couldn't even break this up. Well, actually, that's not true. There's one thing you can do. So in the previous cases, we've had a constant out in the exponent, and we've brought that out. So what we would do here is we could then go the opposite direction. So we could change the constant multiplier out front to be the exponent. Okay. Now 13. The first thing you're going to do, the last thing we did when we're going the other direction, like here, is we had the exponents and we moved them out. So if we have constant multipliers, we need to move them in first. So we don't have any constant multiplier here, but we do here, and we do here. So the first step is we're going to take this 2 and we're going to move it inside and make it an exponent. And likewise here we're going to move it inside and make it the exponent. Now as a review, one other thing too is anytime you have these, if you have logarithms, they all have to be the same base, or you can't do any of this combining. If this were to the base 2 and this were to the base 7, you're out of luck. You're not going to be able to do anything. Okay, then you go, let's go back and see what we did here. So our original problem, number 10, was we had this and it expanded out into that. So what we're trying to do is go back to here. So when we had a positive, it was the numerator, and when we had a negative, it ends up being in the denominator. So that's the same kind of thought process here. So this is negative, so that's in the denominator. These two are positive, so it's in the numerator. So the next thing you do, same base, this is in the numerator, this is in the denominator, this is in the numerator, and then you're done. So we got everything under one log. Okay, 14. So what I would do is I would again take these constants and move them inside first. So the first term, instead of 2 times the natural log of x plus 3, it's going to be the natural log of x plus 3 squared. Here I don't have anything, so it's just going to be the natural log of x. And then the third one's the same case. So it was only the first one that I could move the exponent in, move the constant in, because it was the only one that had a constant. The next one I do is I create a product quotient thing here. The positive ones are in the numerator and the negative ones are in the denominator. So these two are going to be in the numerator, this one's going to be in the denominator. And then we multiply them together. So you'll have x plus 3 squared, numerator because it's positive here. This is positive, so I multiply by x. This is negative, so I divide by x squared plus 1. And then finally I have this coefficient of 1/3, which applies to the whole thing. So then I'll bring this in side, and I'll take everything to the 1/3 power. Like that, and then the whole thing is raised to the 1/3 power. But I could go one step further and say it's the cube root. So I have the cube root of x plus 3 squared times x divided by x squared plus 1. And that's your final answer. So this is equivalent to that. Okay, same kind of deal here for this last one. We're going to take any coefficients in front of the logarithms and move them inside first and make them the exponent. So we have log base 8. Well, the coefficient's 1, so nothing happens to this one. The second one, we have this coefficient multiplier times 3. So we take that number and we move it inside, make it the exponent. The last one doesn't have a coefficient, so we just leave it as it is. Like that. Okay, now we'll combine them all. So we have log base 8. So this is in the numerator. This is in the numerator. This is negative, so it's in the denominator. And then finally, this half can become the exponent. So you'd have log base 8 of y times y plus 4 cubed over y minus 1, the whole thing inside to the 1/2 power. But then you can change the half power back to the square root. So you have the square root of y times y plus 4 cubed over y minus 1. Okay, so next, compare the logarithmic quantities. If the two are equal, explain why. If two are equal, explain why. Okay, because there's 3 of them. It's like the 2, or if 2 are equal to each other. So they all are base to the base 7. Now if I take the first one and I rewrite the square root as the half power, what I'd end up with is 1/2 times the log base 7 of 70, which looks close to that, but it's not right because I've got 1/2 plus, so that's not going to work out. But if we could break this up into, yeah, I don't think that's going to help any. Let's think about this one. So if you take log base 7 of 35, that's log base 7 of 5 times 7. From that, you could break it up into the log base 7 of 5 plus the log base 7 of 7. So that would end up, log base 7 of 7 is 1. So you'd have 1 plus log base 7 of 5. So that's not going to work either. Yeah, to be honest, I don't think any of those are equal to each other, because this half is, I'm trying to think if there's some, oh, that might work. Okay, so let's look at one more case. So if you had log base 7 of the square root of 70, you could say that's equal to the log base 7 of the square root of 7 times the square root of 10. Square root of 7 times the square root of 70. Now that is going to be equal to the log base 7 of the square root of 7 plus the log base 7 of the square root of 10. But the square root of 7 is 7 to the 1/2 power. So you could bring the 1/2 out front. So you'd have 1/2 log base 7 of 7 plus log base 7 of the square root of 10. And the log base 7 of 7 is 1. So you get 1/2 times 1 plus log base 7 of the square root of 10, which turns out these are the same thing. How did I figure out how to do that? Well, here I had square root of 70, here I had the square root of 10. So the only way I could get to the square root of 10 is to break away the square root of 7. And I thought, oh yeah, that's square root of 7 is 7 to the 1/2 power. That's how I can get the 1/2, and then so. Anyway, that's that particular problem. As you can see, I only gave you one of those, but thought you might be interested in how that worked. Okay, so the next one says find the exact value of the logarithm without using a calculator. If this is not possible, state the reason why. So if there's some reason why you can't take the logarithm of the number, state why. So the first one is, this property of logarithms. If you can raise one of these to a certain power with the base being the same base as the logarithm, then you might do some good. So if I rewrite 125 as 5 cubed, what that allows me to do is I could use the quotient rule here, and that would be log base 5 of 1, that's the numerator, minus log base 5 of 5 cubed. So this is the numerator, this is the denominator. You subtract the denominator. The log base 5 of 1 is 0. The log base anything of 1 is 0. Then you could bring out the 3 using that property of exponents. So you have log base 5 of 5. Well, log base 5 of 5, when these are the same, the answer is 1. So you get negative 3 times 1, which is negative 3. Now how would you check this? Because this is log base 5. You could say the natural log of 1 over 5 cubed divided by the natural log of 5. So the base is 5. And if you plug that into your calculator, the natural log of 1 divided by 5 cubed divided by the natural log of 5, I should get negative 3, which is what I do. Yeah, so this would be used in your calculator. You'd have to use a change of base formula. This is not using your calculator. Okay, next one. Log base 4, 16. Okay, so 16 is something 4 raised to some power, which is the second power. So what we could do is we could say that 16 is 4 squared, and then we raise that to the 1.2 power. Now we could use this property of exponents twice, so we could take this outside. So we have 1.2 times the log base 4 of 4 squared, and then you could do it again. So then you have 1.2 times 2 times log base 4 of 4. If you can always get to log base something of something, same number, then that's always going to be 1. So you'd have 2 times 1.2, which would be 2.4 times 1, log base 4 of 4. So you get 2.4. Another way you could have done it is I could have gone ahead and multiplied these together. So when you have x to the a to the b, you multiply the exponents, so you get 2.4. 4 to the 2.4, you can bring that outside. You get the same answer. Now this one you may think, oh, I could rewrite that as negative 3 squared. But the problem is that this is going to be a negative sign. So what I was saying was that anytime you have a negative quantity inside any logarithm, there is no solution, there's no answer. So the logarithm of negative 9 just does not exist. Okay, number 20. So here we have, again, this exponent inside. So what we can do is we can take that outside. So you take 3 and multiply by 4, so you have 12 times the natural log of e. But the natural log of e is just 1. Just like the log base 3 of 3 is 1. This is the log base e of e. So the answer would be 12. So here we have the natural log of the 4th root of e cubed. So one way you could do it is you could change this to a fractional exponent, which would be the other way around. So the numerator is the cubed part, and the denominator is the 4th root. And so you'd bring that exponent out. And again, you'd have the natural log of e, which would be 1. So the answer would be 3/4. 22. Let's see what we need to do with that one. 21e to the natural log of e to the 6th. 21 natural log of e to the 6th minus the natural log of e to the 5th. So again, you could take the 6 out and multiply it. So 6 times 21 is 126. Natural log of e minus, and again bring the exponent out, 5 times the natural log of e. But the natural log of e is 1, so you get 126 times 1 minus 5 times 1, which is 121. Okay, what have we got left here? Okay, so we just got one word problem. So we had a similar situation in the last problem set. In this case, we probably want to use the properties of logarithms, maybe, to help us answer the question. I'm not sure yet, so let's see what it says. Oh, I can't spell psychology. Students participating in a psychology experiment attended several lectures and were given an exam. Every month for a year after the exam, the students were retested to see how much of the material they remembered. The average scores for the group can be modeled by the human memory model. So this is the score. So at t equals 0, you'd have 0 plus 1, and the log to the base 10 of 1 is 0. So this says that the initial score is a 90. And as t increases, you're going to forget stuff, and therefore your average is going to be less. And this is based on from 0 to 12 months. And after 12 months, then you might have to have a different model. So all we really have to do here is just use this equation for these different values. So I'm going to see if I can sneak them in here so I don't have to scroll. So we're saying what is the average score of the original exam? So we just talked about that. So f of 0 is going to be 90. And that's because you'll have negative 15 times the log base 10 of 0 plus 1. The natural log, the log base 10 of 1 is 0, so you get 15 times 0. So ultimately it's 90. So after 6 months, we have to plug 6 into there. Okay, so we're going to evaluate the function at 6. So you'll have 90 minus 15 times log base 10 of 6 plus 1. So let's go ahead and just plug that in our calculator. So this is actually pretty simple. We're just evaluating the functions just to show you that there are models out there that are based on logarithmic results. So we have 90 minus 15 times log base 10 of 6 plus 1, which is 7. So we get an average score of 77.3. And then after 12 months, we've forgotten the most. So you have 90 minus 15 log base 10 of 12 plus 1. So that's going to be, all we need to do is put in 13 into the log base 10 experiment, and we get 73.3. The average gets smaller, or it gets worse. What happens is after 12 months you forget a lot initially, and then as time goes along you forget less, use some certain amount that you retain. So you can see from 0 to 6 months our score dropped almost 13 points, but from 6 months to 12 months it only dropped 4 additional points. So it says, when will the average score decrease to 75? So to solve that, again, I don't want to get in my head of myself here. So what you've got is a score of 75, and that's got to equal to 90 minus 15 times the log base 10 of t plus 1. So what we're doing is we're solving this equation for t. So the way it would work, well, yeah, this is how it works. Luckily, this works out, so it's not that hard. So if you subtract 90 from both sides, you'll get negative 15 on the left-hand side. You get negative 15 here, log base 10 of t plus 1. So if we divide both sides by negative 15, we'll get 1 is equal to the log base 10 of t plus 1. And the question is, what does this argument have to be for the result to be 1? Well, we know log base 6 of 6 equals 1, log base 3 of 3 equals 1, log base 10 of 10 equals 1. What do I need to raise 10 to get 10? Well, it's the first power. So from that, I know that t plus 1 has to equal 10. The argument has to be 10. So that I get a 1 result. So that means t has to be equal to 9. So the answer is 9 months. So that's how you figure that out. Use the properties of logarithms to write the function in another form. So what we could do, let's see, what could we do? We could take the 15. So this is for E. We could take the 15 and move it inside. So you'd have 90 minus log base 10 of t plus 1 to the 15th power, which seems kind of crazy, raising something to the 15th power, but because you're taking the log base 10, it kind of cancels out. You really can't, you'd have to rewrite 90 in terms of log base 10, and you could do that. So the question is, how would you rewrite, the log base 10 of x equals 90? What is x? I think that's the way you would do it, because I'm trying to write this as log base 10. What we'll find out in the next section is you'd say, okay, I'm going to take 10 raised to the log base 10 of x is equal to 10 to the 90th power. And 10 to the log base 10, because those are inverse functions, you get x, so you'd have 10 to the 90th power. So you could write this as log base 10 of 10 to the 90th power. And then you could combine these two. So you'd end up of the log base 10 of 10 to the 90th power divided by t plus 1 to the 15th power. I'm subtracting because I'm dividing because I'm subtracting that. And you still end up with the same result if you plugged it into your calculator, but it's a little bit intimidating. Okay, and then the final thing is to plot what this thing looks like. So, you know, logarithmic function is, well, we, in this case, probably do what we did previously, is, you know, it's going to be, so let's write the function down, think about what's going on here. F of t equals 90 minus 15 log base 10 of t plus 1. And this would be t. And we'll go from 0 to 10. We're actually going to 12, but I'll run out of space. And if we go from negative 100 to positive 100 here, that'll get the values involved. So what we said was that at t equals 0, the answer was 90. And it's going to, what did we see? We said after 6 months, 1, 2, 3, 4, 5, 6, it was 77.3. So that's 10, 20, 30, 40, 50, 60, 70, 70, 73.3, oh, 77.3. In 12 months, which would be about over here, would be 73. So it's going to look something like this. Ultimately, what you have is this negative sign here. So it's, you know, the normal logarithmic function looks something like this. So this is going to go this way. It's going to be shifted 90 units in the y direction, positive, and then it's also going to be stretched. So that's probably why it's just best to plot those 3 points and call it a day. We also said after 9 months, I guess it was, that we were at 75. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and that was 75, which is about right there. So it all fits in there nicely. Okay, so that's it.